as close to as smart as we think we are.
A big step forward in your measurement capability in the way that JWST has done for astronomy.
We are heading towards the second anniversary of the launch of the James Webb Space Telescope, and only in the first 20-odd months since it started its science operations, it has changed our perception of the universe forever. Not only that, the telescope is also troubling scientists big time by pointing out flaws in our cosmology. Scientists don't know exactly when the first clumps of stars began to merge into the beginnings of the galaxies we see today, but cosmologists previously estimated that the process began slowly taking shape within the first few 100 million years after the Big Bang. Currently accepted theories suggest that these early proto-galaxies reached adolescence 1 to 2 billion years into the universe's life, forming into dwarf galaxies that began devouring each other, to grow into ones like our own, the Milky Way. The cosmic dark ages, we believed, was a time when the universe was enveloped by a fog of neutral hydrogen that trapped the light of the first stars and galaxies. According to the Standard Model, the fog didn't lift until 1 billion years after the Big Bang, when the neutral hydrogen had been reionized and once again split apart. And with the end of the Dark Ages, the first stars began to come together to form galaxies, thereby slowly changing the universe to what it is today. That is what our models stated, almost all of them. Then, we launched the James Webb Space Telescope, and suddenly, we found ourselves in a conflict that threatens to change our very understanding of the cosmos. The discovery of thousands of unusually bright early galaxies by Webb, some even resembling our own, came as a bewildering surprise for astronomers. It was a discovery that put their most basic understanding of how the universe evolved into severe doubt. If these galaxies were like ours, to glow so bright they would need to have swollen to enormous sizes in a fraction of the usual time. Typically, a galaxy is bright because it's big. But because these galaxies formed at cosmic dawn, not enough time has passed since the Big Bang. How could these massive galaxies assemble so quickly? And how are they so bright that they theoretically shouldn't exist? Scientists have come up with a phrase for these galaxies: too big and too soon. The brightnesses of their magnitude should only come from massive galaxies with as many stars as the Milky Way, yet, these early galaxies, somehow, took shape in a fraction of the time that ours did. That left scientists scrambling for an explanation while questioning the basic tenets of cosmology. A team of researchers decided that it was time we let a supercomputer get to the bottom of this, because clearly, scientists are at their wits' end. To investigate what could have given these galaxies their strange sparkle, the researchers created a model of galaxy formation and ran it through a supercomputer, simulating the swirling, clotting gas of the early universe as it turned into stars, which in turn formed into galaxies. By carefully accounting for the mass, energy, momentum and chemical composition of the young universe, the researchers found that stars at this early time could have formed in sudden, rapid bursts after years of quiescence. Known as bursty star formation, the process is unlike the steady rate of star birth in today's universe and could explain why the early universe is so bright. And so, the researchers concluded that the bright galaxies found by the James Webb Space Telescope in the very early universe could be the product of bursts of massive star formation, and it's likely that this fact renders the galaxies more luminous than expected for the era in which they exist. In other words, the universe went through a sudden let-there-be-light moment. When the JWST began science operations in the summer of 2022, its deep observations of the universe quickly began turning up high redshift galaxies. In fact, the galaxies, which were seen as they were when the universe was less than 400 million years old, appeared more luminous than what the Standard Model of cosmology predicts for the era. This led to claims that the Standard Model, which depicts galaxies starting off small and then growing hierarchically through mergers driven by filaments and halos of dark matter in the cosmic web, must be wrong. By drawing results from the simulation, scientists now believe that a galactic system doesn't need to be that massive. If star formation happens in bursts, it will emit flashes of light. That is why we see several very bright galaxies. Most importantly, the results from the new simulations fit with the hierarchical growth model of galaxies as depicted in the standard model of cosmology. But the problem with the standard model doesn't end here. There are several ways the James Webb Telescope is pointing towards major flaws in our models. Number 1. Extremely early galaxies. Keep in mind that we are talking in terms of cosmic timescale, so when you have a galaxy forming only a few 100 million years after the Big Bang, it's like it happened instantaneously. So, the Big Bang happened approximately 13.8 billion years ago, and according to the model, for the first 1 billion years, galaxies did not form. However, the James Webb Space Telescope has shattered that belief. We have found galaxies at the edge of the universe, fully formed and massive. The oldest galaxy we have found using the telescope so far is Massey's galaxy, which existed when the 13.8 billion-year-old universe was just around 390 million years old, which is incredibly young for our cosmic expanse. Not to mention that Massey's galaxy is one of the many candidates that Webb has spotted, and more research and observation can reveal galaxies that existed even earlier than that. Number 2, scientists just discovered two massive objects collided very early in the universe. That's right, just when cosmologists thought they had a workable theory for when and how galaxy collisions happened in the early universe, the James Webb Telescope challenges them again. In this case, the challenger is a collision of two massive galaxy clusters that combine to form a gigantic galaxy cluster. They happened when the universe was half its age, and according to our cosmic model, that's too early. The result of the collision is the El Gordo galaxy cluster. And its existence challenges the Big Bang like never before, because according to it, galaxies form first in the universe. Then later on, they begin to combine to create larger galaxies and clusters of galaxies. That takes time, so having them show up so early, as El Gordo did, in cosmic history is a big problem. One question that will need to be answered is whether or not this massive early collision points towards the need for a new model, or changes to the existing one. Number 3. Giant black holes near the birth of the universe. When the James Webb Space Telescope stared at young galaxies, which appear as mere red specks in the darkness, it saw a surprising number with cyclones churning in their centers. Yes, an abundant population of sources scientists didn't know about, or didn't anticipate finding at all. The most straightforward explanation for the tornado-hearted galaxies is that large black holes weighing millions of suns are whipping the gas clouds into a frenzy. These are the ancestors of supermassive black holes that seem to appear in the cosmic record inexplicably early. By studying these record-setting youngsters discovered this year by Webb, scientists hope to learn where the first humongous black holes came from, and perhaps identify if they grow extremely rapidly, or were they simply born big. Yet the observations are also perplexing because astronomers expected Webb to find many smaller but hungry black holes, but instead, they uncovered a throng of bulky black holes that may rewrite our established theories of stars and galaxy formation. Number 4. Heavy elements missing. Not only did the Webb telescope find extremely massive early galaxies, it also discovered that those galaxies defy rules. A team of astronomers used the JWST to gaze over 12 billion years back in time and observe galaxies as well as the rules they followed through cosmic history. The most surprising discovery was that ancient galaxies produced far fewer heavy elements than we would have predicted, based on what we know from galaxies that formed later. This disparity hadn't been spotted before because instruments used prior to Webb hadn't been powerful enough to see the chemical makeup of galaxies as far back as around 11 billion years ago. The James Webb Telescope, however, allowed this team to look back to just a few 100 million years after the Big Bang, which showed a break in the relationship between star formation, mass, and chemistry. Number 5. The Hubble tension. The Standard Model, which is the bedrock of essentially all research in the field, dictates that there is a fixed and precise sequence of events that followed the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then, the force of gravity pulled together the stars into galaxies. Yet, the data relayed by Webb introduced a jarring twist in this cosmic narrative. It unveiled the existence of exceptionally large galaxies that seem to form with astonishing speed, defying the timelines prescribed by the Standard Model. This finding wasn't a minor discrepancy, and to make matters worse, the conundrum surrounding the Hubble tension remained unsolved. At first, scientists hoped that these discrepancies would be resolved as data got more accurate with more observations. But not only has that not happened, the discrepancies have gotten far more precise, and the recent data from Webb has added salt to the wound. While these revisions may have been essential and scientifically sound, in light of the current challenges, they appear as a series of conveniently tailored adjustments. Physicists and astronomers are starting to get the sense that something may be really wrong. Number 6. The universe might be twice as old. Okay, picture this. Our universe is not the spry 13.7 billion-year-old entity that we once believed it to be. Instead, it could be a grand 26.7 billion years old. Yes, let that sink in for a moment. This finding, according to a new study by Rajendra Gupta, adjunct professor of physics at the University of Ottawa, fundamentally changes our understanding of the universe, and may solve the puzzle of the impossible early galaxy problem. For years, we've been estimating the age of the universe using two primary methods. First, by calculating the time that has passed since the Big Bang, the colossal explosion believed to have birthed our universe. And second, by studying the oldest stars, based on the redshift of light coming from far-off galaxies. The redshift phenomenon happens when light from an object moving away from us stretches towards the red end of the light spectrum. By measuring this redshift, we've been able to calculate the age of the universe. In 2021, using a model called the Lambda-CDM concordance, scientists estimated the universe to be about 13.797 billion years old. But there's a problem. Some stars, like the Methuselah, appear to be older than the universe itself. And that's not all. The James Webb Space Telescope has discovered early galaxies that seem to be far too advanced for their age. These galaxies were around just 300 million years after the Big Bang but had the mass and maturity typically seen in galaxies billions of years old. What's more, they're much smaller than we'd expect, adding another piece to the puzzle. This is where Fritz Zwicky's tired light theory comes into play. According to this theory, the redshift we see might not be due to galaxies moving away from us. Instead, it might be because light loses energy as it travels across the universe. For a long time, this theory conflicted with what we saw in the universe. But according to Gupta, if we let this theory coexist with an expanding universe, we can reinterpret the redshift as a combination of both these phenomena. But Gupta didn't stop there. He also introduced a new idea based on physicist Paul Dirac's hypothesis about coupling constants. These are fundamental physical rules that control how particles interact. According to Dirac, these constants might have changed over time. If we let these constants evolve, then the time for early galaxies to form extends from a few 100 million years to several billion years. That could explain why the galaxies we see are so advanced for their age. Finally, Gupta challenges the traditional interpretation of the cosmological constant. This represents dark energy pushing the universe to expand faster. Instead, he proposes a new constant that accounts for the evolving coupling constants. This change could help us understand why the early galaxies were smaller than expected. It also offers a more accurate picture of the universe. In the words of Gupta, our newly devised model stretches the galaxy formation time by several billion years, making the universe 26.7 billion years old, and not 13.7 as previously estimated. Now the James Webb Telescope is expected to run for a decade or two, and who knows what intricate details it is going to find out about the origin of the universe that is going to help answer a lot of the questions that currently we don't have the answers to. What do you have to say? Please share your valuable comments